This is a reminder, Class Connect sessions are recorded and distributed for learning purposes that are listed here. As always, be respectful, appropriate, and please participate in class, but please don't share personal information like contact information or social media stuff during class for your own security reasons. All right, everyone, so we should be in our November 13th attendance ticket. Again, you just need to have it open and ready to go. You will be getting the answers in class, but you need to have it open. So link is in the chat box. Password is there as well. I need green checks all around if we've got it open. Red X's if we're confused about anything. We do have some new students today. So if you're a new student and you're confused about anything, please, please, please let me know. Still waiting on green checks. Let's see here. Adrian, Adriana, Annalise, and Dalen, Destiny, and let's see here. Gabe, Josh, Kyrie, Kendra, Kevin, Rachel, Ricky, and Ty. Green checks. Looking good. No, Stephen, game day is tomorrow. Yeah, game day is tomorrow for Unit 2. Looking good, looking good. Just waiting on a few more green checks. Awesome. Hi, Jackie. Looking good. All right, let's go ahead and keep on going. Okay, so today we are working on our phase change lab. So if you're a new student, don't freak out. We do go over all this information in class, so don't worry. You will definitely be able to complete the lab, and it's important you do. Labs are 25% of your grade, so they're super important. But we're going to go ahead. We're going to do our lab today. Tomorrow we will have finished up Unit 2, so we will have a Unit 2 game day to review all of our Unit 2 information. But we do need to make sure we do need to make sure that you participate in the game tomorrow in order to get extra credit. Okay, and then Thursday, oops, I forgot to change the dates up here. Oops, oh good. Thursday, Friday, we will be starting our new unit, so we'll be in unit number 3, talking about gases and gas laws. If you're a new student, please remember, please be aware that this is my contact information up here, so this is my email and my phone number that you can call or text, and please be aware that you do get 5 attempts on every assignment, so if you ever don't do well on something, always try again. You can get a higher score, and you can always come to support sessions as well, and I can help you get higher scores on things. So definitely always try again. And this is me over here with my family. This is my husband and my daughter. She just turned 13 months yesterday, guys. A year and a month. Oh my gosh, getting old so fast. I can't handle it. All right, so that being said, again, we do have some new students, so go ahead, give a round of applause to our new students, welcoming them to class. Yes, welcome to class. So if you are a late start student, meaning you're starting today, please be aware that you will be excused from week 1 and week 2 assignments. You should already see that in your grade book. You'll see that you are excused from those. Again, we are doing a lab report today, but I am covering all the information you need to know in class. So you still do need to complete it, even if you're a new student, because again, we're doing everything together. We should be able to complete it. And if you're a new student, please be aware that you do have a survey due tomorrow as well. Just because tomorrow we don't have any other assignments because it's just an extra credit game day. So I moved that survey so that it's tomorrow. Okay, smiley faces everyone if that makes sense. Looking good. Awesome. Okay, perfect. So one more thing. Again, today we are doing our lab. At this point, that means that we'll have done 2 labs, and that means that each of those 2 labs is therefore half of our 25%. So each lab therefore is 12.5% of your grade currently. So please make sure that you complete your labs because 12.5% is a pretty big percentage. Smiley faces if that makes sense, right? Awesome, Stephen. Looking good. So make sure you guys do your lab reports, and also if you're a new student, please make sure you complete STAR 360. You will be getting an email with instructions on that. It's just an assessment just to see kind of where you are math and reading wise. We don't grade you based on how well you do. We just grade you on whether or not you complete it. So just make sure you get it done. That way you can get 50 points. It's a huge part of your grade. You do want to make sure you still kind of do well though, so still do your best, because if you do better, you don't have to go to as many live sessions, and attendance is required to our classes, so if you have to go to more of them and you miss sessions, that means your grade's going to be a little bit lower. So try to do your best so you don't have to go to as many classes. Cool. Okay, guys, so we are in Unit 2. We've been talking about phase changes and the states of matter. We've been talking about heat and energy and thermodynamics. Today, we are working on a lab. So as always, our labs, we design an experiment based on a hypothesis, and we graph and analyze that resulting data. Specifically, our lab today, though, is taking a look at phase changes and how energy is gained or lost during a phase change. Okay? So let's do some really quick review. Remember that when we have a state of matter, whether it's a solid like ice or a liquid like liquid water or a gas like steam, the molecule itself, the H2O molecule, is not actually changing. Smiley faces if that makes sense. Okay, the molecule itself is not actually changing. Okay. Looking good, looking good. Awesome, awesome, awesome. So that being said, guys, if we think about ice and water and steam, are they all still H2O? Tell me in the chat box. Are the molecules in ice, the molecules in water, the molecules in steam, are they all identical? Are they all still H2O? Yeah, exactly. So they're all exactly the same molecules. The only thing that's changing is how they're interacting with other molecules. So this is the difference between like you are always yourself, but how you interact with your family and your friends and your enemies or your frenemies may be different, right? So how you interact with other people is different depending on who they are, right? So with solids, remember those molecules, those H2O molecules are still H2O. They're just kind of vibrating in place. No, Stephen, OxyClean is actually a type of oxygenated bleach. So I can tell you more about that later. I don't know the exact chemical, but it's definitely not water. Cool. Okay, so in solids, the molecules, those H2O molecules, are just kind of sitting in their seat, kind of shaking back and forth, vibrating in place, which is why we don't see solids move from outside of them, right? So on an atomic level, they're moving, but from our perspective, they don't look like they're moving. They're just staying in place. Liquids, on the other hand, those molecules can move a little bit more freely, and so they can actually flow around, which is why liquids can actually flow to spread out along the bottom of a container. And then gases have really fast moving molecules that are moving so fast that they can actually escape from each other and they can actually expand to leave a container as long as the container is open. Okay, thumbs up guys from your smiley face menu if all of that makes sense. Right, so solids, they're vibrating in place. Liquids, more energy, can flow around. Gases, lots of energy and can escape. Awesome. Let me go ahead and demo this for you. So I want to go ahead and show you guys some examples of this. So give me a smiley face if you can see me here. Can everyone see me? Looking good, looking good. All right, so I feel like I'm missing something. Where is my thermos? Okay, sorry guys. Hold on one second. I will be right back with my thermos. Okay, there we go. Once more. Smiley faces if you can see me, guys. Sorry, I realized that I was missing one of my supplies. Cool, okay, so let's go ahead and prove to ourselves that this idea of molecules just kind of moving at different speeds are what are causing these different temperatures, these different kind of phases, okay? So let's see here. Right here, I'm going to go ahead and I'm going to be putting, let's go ahead and do it this way, okay? So in one of these, I'm going to go ahead and be putting ice water, okay? So right here, this one will be ice water, okay? And then over here, I'm going to be putting room temperature water, okay? And over here, I'm going to be putting boiling water, okay? Smiley faces if that makes sense, what we're doing so far. So ice water right here, room temperature water here, and over here, we've got boiling water. All right, so let's go ahead and do that. So here is my ice water, which is water that's been on ice for quite some time. And then over here, I've got my boiling water. And then in the center, I'm going to go ahead and put my room temperature water. Okay? And what we're going to be doing is we're going to be putting some food dye in them. This is actually kind of an experiment that we did in our last quarter class. If you were with me last quarter, this should be pretty similar. But it's this one is actually showing all three temperatures. Okay, so again, cold, right? We've got, sorry, let me see if we can get that a little centered. Cold right here, room temperature here, and hot here. Okay, so let's go ahead. We're going to put some dye in each of these, and we're going to see what happens. Okay, so here's our hot one. Okay, tell me what observations are you making in the chat box? in the chat box, what observations do you make about what's happening with the dye there? Tell me in the chat box. What observations can you make? Again, this is hot, this is room temperature, and this is cold. What do you guys see? In which one is it moving fast, though? Yeah, we got to be a little bit more specific. So which ones are moving at which speeds? Yeah, okay, so yeah, definitely the hot one, the dye definitely spread the fastest, right? Super, super fast in our hot one over here, right? What about the cold one versus the room temperature one? Do we notice any differences between the cold one and the room temperature one? Tell me in the chat box. What do you guys see? Yeah, this cold one is definitely taking a whole lot longer to mix, right? This one's definitely taking way longer to mix. The room temperature one, it's sort of mixing, right? It's sort of missing. It's not actually a solid, right? It's just really close to being a solid just because it's really cold, right? This was water that was in ice, so it was really cold, but it's not actually a solid right now. Yeah. Okay, but yeah, it's definitely taking way, way longer. So what does that tell us, guys? In cold substances, almost to solids, in cold substances, are the molecules moving fast or slow? In cold ones like this one, are the molecules moving fast or slow? Tell me in the chat box. Yeah, they're moving really, really, really slow. Exactly. They're moving really, really, really slow. What about in our normal run, our room temperature one? How are the molecules moving in our room temperature one? Yeah, they're still moving pretty slow, but they're definitely moving a little bit faster, right? Because the dye is starting to mix definitely a little bit faster than in our cold one. And then what about our hot one over here? How's the dye moving in the hot one? If we actually zoom in, you can actually see there is still some dye there. I don't know if you guys can tell. There is still some dye just floating around there. Yeah, but this one is definitely much, much, much faster. Exactly. Good. So that definitely shows us something that we've learned, right? That even though all of these are water, they all act a little bit different just because their molecules are moving at different speeds, right? Slow, medium, and fast. Okay, smiley faces if that helps us better understand this idea of molecules and their phases, molecules and their states. Awesome. Okay, guys. So this is number 1 in your attendance ticket. Again, the link is in the link is in the chat box. All right. So go ahead. Answer number 1. You need to fill in the blank with the word interacts. Okay. So go ahead. Give me a green check when you have that saved. Everybody has 30 seconds. Ready, set, go. If you're a new student and you're confused, please let me know. But most of us are on our game, so most of us should know what we're doing. Go, go, go. All right, just waiting on a few more green checks. So Annalise, Sienna, Dalen, and Gade, Jacob, Jasmine, Josh, Kyrie, Saul, and Ty. Green checks if we're good on number 1. Perfect. Let's keep on going. Okay, guys. So the next thing that we need to talk about, right, those were the states of matter, solid, liquid, and gas. However, we can actually change between solids, liquids, and gases, right? Think about how we go from ice to liquid water. Tell me in the chat box, how do we go from ice to liquid water? How do we go from ice to liquid water? Yeah, we add heat, exactly, just by heating it up, right? If you take ice out of the freezer, it begins to heat up, it turns into a liquid. Let's say we add a whole bunch of heat to it by like putting it on the stove. What eventually happens? If we add a whole bunch of heat and add it to the stove, it begins to boil, it begins to turn into steam, which is a type of gaseous water. Exactly. Now, these are all what are called endothermic phase changes, right? We've learned about both exothermic and endothermic, but today we're specifically looking at the endothermic phase changes, which are the phase changes that take in heat, right? So we absorb heat, and as a result, the substance gets warmer, right? Think about if you are water and you're absorbing heat, you're going to get warmer. And since you're getting warmer, you're getting more energy, and so your molecules start to speed up. Smiley faces if you can see that here. The solid is gaining heat, which increases its temperature, which increases its motion. The liquid gains more heat, increases its temperature, and increases its motion. Okay, so this should make sense, right? Because when we're melting something, going from a solid to a liquid, right, we go from very low energy molecules to medium energy molecules, just like we saw in the, no worries, Seha, link is in the chat box, just like we saw in our demo, right, where in our cold one, it moves very slowly, in our medium one, it moves a little bit faster. So since we're getting energy, we're speeding up, okay? You can see those molecules move around more. Or Again, if you go from evaporation, a liquid to a gas, you're going from medium energy to very high energy, almost boiling, right? So these are boiling, and so you're getting steam. And so they get lots and lots of energy, and they can speed up, move really fast, and move away from each other. And then sublimation. Sublimation is if we actually just skip this right here. Remember, guys, what was my example of sublimation, where you go from a solid to a gas? It's a really cool thing that you can like put in your drink, and it makes it look like witch's brew. Yeah, dry ice. Yeah, so dry ice is a solid that you can put into water, and it immediately turns into a gas, which creates fog. Smiley faces if you guys know what I'm talking about. It creates really cool fog kind of looking stuff. Yeah. If you haven't, yeah, it's not the same as ice. It's ice, carbon dioxide. It's not iced water, right? But what happens here is same thing. We're going from low energy to high energy, so it's endothermic. It's absorbing lots of heat really, really fast, getting hotter, speeding up, gaining energy. Awesome. Okay, let's make sure that this makes sense. Grab your polling tools. So your green checks just turned into a polling tool. Tell me, endothermic phase changes like melting, evaporation, sublimation, they absorb heat, which results in what? Slower molecules with less energy, slower molecules with more energy, faster molecules with less energy, or faster molecules with more energy. If we are changing them, adding heat, what's happening to the molecules? Yeah, you can use it to make ice cream. Yeah. A lot of times, though, they actually also use liquid nitrogen to make ice cream. Liquid nitrogen is a popular one to make ice cream because liquid nitrogen is super cold as well. Cool. Awesome, guys. Grab your polling tools. Let's look at it. Think about if we are becoming hotter, right? Melting, evaporating, sublimating, getting hotter. What are those molecules doing? Do you think they're getting faster or slower? Do you think they have more or less energy? Awesome. About 5 more seconds. Use your polling tools quickly, quickly. Yeah, liquid nitrogen is not quite as easy to get as dry ice. Still possible, though. Cool. All right, guys. So I'm looking at this, and most of us are saying letter D, and letter D is correct, right? Think about if you're going from a solid to a liquid to a gas. Remember, the gas one is the hotter one, and we just saw that hotter substances are the molecules moving faster or slower. In hotter substances, are they moving faster or slower? Tell me in the chat box. We just saw it, right? That hot water with the dye, yeah, it's moving a lot faster, which also means if you're moving faster, do those molecules have more or less energy? When molecules are moving faster, do you think they have more or less energy? Definitely more energy. Definitely more energy. Perfect. Okay, this is number 2 in your ticket. Go ahead, give me a green check when you have it saved. The answers are randomized, so make sure you read carefully. Make sure you choose the correct one because they are in random order. 30 seconds, ready, set, go. Okay, just waiting on a few more green checks. Adriana, Annalise, and Gabe, Haley, Jacob, Jackie, Jasmine, Jeremy, Tucker, Josh, Julie, and Kyrie, and Kevin, Saul, Sophia, Ty, green checks if we're good on number 2. Again, make sure you save number 2. Awesome. Let's keep on going. Okay, guys, so at this point, we can kind of jump into our lab because we know enough now in order to understand what our lab is all about. So today, we're going to take a look at how temperature is related to phase changes. So we're going to take a look as we change phases going from solid ice to liquid water to gaseous water. How is the temperature changing? So that's what we're going to take a look at today. Okay, so here's the thing, guys. Remember, this is our scientific method. If you're new with us, this should hopefully still look familiar, but our scientific method has a few steps, right? We make observations about the world around us. We ask questions about why that happens. From there, we can form a hypothesis, which is an educated guess or an answer to our question that we think might be correct. Based on that hypothesis, we perform an experiment. From that experiment, we get some data, so we can gather that data and analyze it. And then based on our data, we can draw our conclusions. We can say, was our hypothesis wrong? In which case we need to go back, change our hypothesis, and try again. Or was our hypothesis right? And what can we go on and tell the scientific community about that? Okay, smiley faces if that makes sense. Again, I know there's a few new of you, but a bunch of you have already seen this. This should be pretty familiar. Okay? Again, this is how we're going to investigate the world around us. This is how we're going to investigate our lab today. Okay, so Remember, we use our five senses to make observations. So we know the five senses. Who can tell them to me really quickly in the chat box? We know what the five senses are. Yes, we've got sight, absolutely. Yes, we've got hearing. Definitely have that one. Yes, nose is smelling. Perfect. Next one. Yes, taste. Exactly. And the last one here we have is, yes, touch. Perfect. Okay, so using our five senses, again, we can make observations about the world. Now, in this case, you're going to go ahead and make an observation based on a video that you're watching me. Please don't try to taste your computer, okay? So there are only a couple senses you're going to be using right now, right? You'll use sight, you'll use hearing, right? You won't really be able to smell, taste, or touch, right? Otherwise, your computer may get a little damaged. So let's go ahead. I'm going to go ahead and start our video here. Again, go ahead, give me a smiley face if you can see me. Awesome. Okay, guys, so here I have some ice. Okay, so I don't know if you guys can see this, right? So right here I've got some ice in an insulated container, okay? And over here I have the water that we just used, right? So actually, sorry, I'm gonna, no, that'll work. I'll use this water, right? So this is the water that we just used. It's room temperature, okay? So do you guys know what room temperature is about? Tell me in the chat box. What temperature do we usually consider room temperature to be? Think about what temperature your house is right now. No. Yeah, it's usually around like 72. Yeah, so room temperature is usually about 72. In my case, this is probably a little bit colder. My house is a little bit colder right now, but it's probably still pretty close to 70. Okay, so we've got our room temperature water right here, and we've got our ice right here. Do you guys know what temperature is ice? Tell me in the chat box. What temperature is ice? What's freezing? What's the freezing temperature? Yes, 32 degrees. Today we're talking about Fahrenheit right now. Eventually we will switch over to Celsius. So right now this is about 32 degrees Fahrenheit or 0 degrees Celsius. Okay, so two different scales, right? 32 Fahrenheit, 0 degrees Celsius. Same thing. Over here, again, this is 70 degrees Fahrenheit, about 20 degrees Celsius. About 20 degrees Celsius. Okay, so let's go ahead and combine them together. And I want you guys to tell me, what temperature do you think that this mixture is going to be now? What temperature do you guys think this mixture will be? If I'm mixing together 70 degree stuff with 32 degree stuff, what temperature do you think this is going to turn out to be? Tell me in the chat box, right? I can write this on the board, right? We've got 70 degree water and we've got 32 degree ice. Again, this is in Fahrenheit. And again, this is in Fahrenheit. Yeah, so I think a lot of us think, right, that they would probably average out, right? So averaging out, you know, around 50 or like 51-ish, right? About halfway between 32 and 70. Smiley faces if that makes sense. If that makes sense why we're predicting that. Right, they're about halfway through. Cool, cool, cool. All right, guys, so I'm going to go ahead and I'm going to actually put a thermometer in here, and we're going to go ahead and see what the actual temperature is. Okay, it might be a little bit hard to see. Let's see if we can get this to work. Okay, I don't think you guys are going to be able to see the temperature super well. Can anyone tell me if they can see that? It's probably pretty blurry for you guys. No, yeah, definitely pretty blurry. Okay, well, I'm taking a look at this right now, guys, and I'm looking at it, and it says 32 degrees. Is that what you guys expected? Did you expect this water to be 32 degrees? No, that seems super weird to us, right? Yeah, so tell me, what observation can you make here? What observation can you make here? Based on what we just saw, what observation can you make? Because that's definitely super weird. It's definitely not something that we were expecting. Yeah, it's actually super, super close to the ice temperature, right? So that seems really bizarre to us because we feel like most of the time when we mix two things that are different temperatures, they equalize out, right? That's what we've learned in the past, right? Yeah, so the water actually goes to the temperature of the ice and not the other way around, right? So that's an observation that we can make, right? When we have ice water, the water actually goes to the temperature of the ice, not the other way around. So, right, it goes down to 30 degrees Fahrenheit or 0 degrees Celsius. Okay, so that's kind of a crazy observation. And today we're going to learn why that happens. Okay, so again, this is where we're starting. Seems kind of weird. So let's turn this into a question, right? So today we're talking about phase changes and temperature. So we want to see, how do phase changes, in which case, what phase change are we undergoing right now? What phase change is happening in my little cup here? Tell me in the chat box. What phase change is actually going on in here? It might be hard to tell unless we take a super long time, but what phase change is happening here? Tell me just the simple one, right? Like evaporation or boiling, or what is happening here? Nuclear winter, no. Yeah, it's melting, right? Smiley faces if that makes sense. The phase change that we're undergoing right now is melting. So phase changes like melting, we want to know how that's related to the temperature, right? Because it seems super weird that during a phase change, it's actually 0 degrees Celsius or 30 degrees Fahrenheit, when we would have expected it to be somewhere between normal water and normal ice, right? Smiley faces if that makes sense, why that's our question today, because it seems super weird. Why did it go down to the temperature of ice, right? Cool. Okay, guys, so I'm going to go ahead and turn off my video, and let's go ahead and jump into that. So really quickly, I do want to make some real life connections. Tell me in the chat box or using your green checks, who enjoys cooking? What do you enjoy cooking? Tell me in the chat box, who enjoys cooking? What do you enjoy cooking? Like I said, I made some Salvadorian tamales last night. Those were super delicious. Yeah, lasagna. Lasagna's a tough one. It takes so many steps. I feel like, I guess, tamales take a lot of steps too. Pasta and veggies, yes, chili verde, cookies. Cool, awesome. Okay, so here's the thing, guys, though. When we cook things, is it important? Think about meat. Is it important for that meat to reach a certain temperature when we cook it? Yes, it's super important. And why do we need our meat to reach a certain temperature? Tell me in the chat box, why do we need our meat to reach a certain temperature? Yeah, to kill bacteria, to kill fungus, right? To kill anything that might be inside of that meat, right? Yeah, so it's cooked, right? If it's not cooked, we can be in danger of getting food poisoning, right? I know I saw in the news recently that there was a recall on some turkey because people were getting salmonella poisoning, which, guys, you don't get salmonella poisoning as long as you're very clean and as long as you cook your turkey. Okay, so just make sure you don't touch your mouth or touch other things in your kitchen when you touch raw bird. Okay, that's the best way to avoid salmonella poisoning. Okay, but again, food needs to be cooked to certain temperatures. And again, what instrument do we use to measure temperature? In general, of foods or of other things, what instrument do we use to measure temperature? Yeah, and make sure, yeah, you use soap when you wash your hands. I see one person knows. What do we use to measure temperature? Yeah, a thermometer, exactly. Now, the thing is, when you get thermometers from the store, at some point your thermometer will probably become a little bit wonky. It won't go to the perfect temperature, and that's actually really bad. You don't want your temperature to be wrong, because if your temperature is wrong, then you could be at risk for food poisoning. So what you can do is you can actually calibrate your thermometer by using ice water, because we just learned that ice water is always 0 degrees Celsius or 32 degrees Fahrenheit, right? It's always at freezing, okay? Even though it's both ice and water, it's technically always at freezing temperature. And so because it's always at freezing temperature, we can reliably use ice water to recalibrate our thermometer, right? You can take your thermometer, put it in the ice water, and reset it to 0, because we know that that's truly 0 degrees Celsius. Smiley faces if that makes sense. Steven. Yeah, exactly. That's super, super dangerous, right, Sarah? Oh, that's so scary. I'm glad you're okay, because that's really dangerous. I love sushi, and I would cry if that happened. Yeah. Well, so again, we just learned, Tucker, that based on what I just demoed to you, that ice water and ice are actually the same temperature. They're actually both 0 degrees Celsius or both 32 degrees Fahrenheit, right? So that's what we're trying to figure out today, is why does that happen? Why are they both the same, even though we think that ice should be colder? Okay? Cool. All right, so let's jump into that. So again, oh, sorry, this is just a picture of this, right? So you can use the ice point method in order to calibrate thermometers. Again, if you have ice and water and you put them together, the ice water will be at 0 degrees or 32 degrees Fahrenheit. So by putting your thermometer in here and recalibrating it to that 0, you know that it's truly you know that it's truly 0, you know that it's truly calibrated. Okay, so just in case you ever need to know that for the future when you're cooking your food and you don't want to die. Okay, so here's our observations, guys, right? We observed that when water melts, it goes from a solid to a liquid, right? But it seems to stay at 0 degrees Celsius. And we want to know, how does the temperature change during those phase changes of water? Okay, so our hypothesis today, we need to make a hypothesis out of this. Okay, so let's take a look at this. If the substance goes from solid to liquid, like water, if water goes from solid to liquid, what do you think happens to our temperature? In general, if we go from a solid to a liquid, what do you think is happening to the temperature? What do you think is happening to the temperature? Yeah, we can say that it gets warmer, right? Then the substance gets warmer, right? So temperature increases, right? Smiley faces if that makes sense to you. That makes a lot of sense to me, right? As we go from solid to liquid, it should get warmer. Cool. Okay. Now, that being said, guys, all right, I'm going to go ahead and send you really quick your lab report. All right, please go ahead and open up your lab report. We're going to answer question number 1 together. Okay, so here's the link to the lab report. Again, we're answering question number 1 together. Green checks when you have that open. Green checks when you have that open. Steven. No, rises is still correct. You can say temperature rises or it gets warmer. That's both correct. You're totally fine. Looking good. Again, make sure you open up your lab, guys. You should still have your attendance ticket open. Yeah, Ariana, you can take pictures. If for some reason you can't open 2 things at the same time, you guys can just take pictures so that you have the answers. Cool. Okay. So that being said, guys, if water changes phases from solid to liquid over time, then the temperature will increase. That's our hypothesis. Okay. So let's talk about our independent variable. In this case, our independent variable isn't so much what we're changing, it's what we're letting happening, right? So we're going to have some water out on the table and we're going to let it just sit there for a long time. Okay. So in this case, our independent variable is actually time. Okay. And today it's going to be in minutes. Smiley faces if that makes sense. Okay. Because we can't really control phase changes, but we can control how long we watch it for, right? So we can control the time that we're watching it for. Now, our dependent variable, that's what we're measuring at the end. That's the data we're trying to collect. And take a look at the end of our hypothesis. What am I trying to collect here? Again, the beginning of the hypothesis is always the independent variable, and the end of the hypothesis is always the dependent variable. So in this case, what's our dependent variable? Tell me in the chat box. What am I measuring here? If water changes phases from solid to liquid over time, then temperature will increase. What am I measuring at the end of my experiment? Awesome, I got an answer from Mikey. I see some other people typing. I see Sally typing, Sienna typing. Yeah, exactly, guys. We are measuring temperature, right? So today we're going to be measuring temperature, and today it's going to be in degrees Celsius, just because that's what we measure in science is with Celsius. Okay, guys? So this is exactly what you need to copy into question number 1. Okay, so please go ahead and answer question number 1 and give me a green check when you have number 1 saved in your lab report. Again, we are currently in the lab report. Green checks when we have number 1 saved. You guys have 60 seconds. Ready, set, go. All right, still waiting on a few more green checks. So Adriana, Andres, Angelina, Annalise, Ciara, Dalen, Destiny, Diego, Gabe, Haley, Jacob, Jackie, Johnny, Josh, Julie, Kyrie, Kendra, Kevin, Ricky, Saul, Seha, and Ty. Again, guys, if you need to, you can always take a picture. If you're a slow typer, take a picture, but still give me a green check, even if you take a picture. Cool, guys. All right, let's keep on going. Okay, so that's number 1 in our lab report. There's only 3 more questions in the lab. So here's what's going to happen, guys. All right, I'm going to be going... I'm going to go ahead and give you the link to the lab video. Okay, so the lab video is going to show you what they did in the experiment. Okay, so I'm going to go ahead and give you this link. Okay, so please make sure you open that up. All right, so this is the link to the video. I'll also include it in the recording. But that's the link to how they did the experiment, okay? So once you watch that video, you'll understand how they got the data that they got.
I'm Pat Keeney, an instructional designer with K-12. Along with my assistant, we're here to work with you on a lab that explores changes of phase. In most lab work, advanced preparation is needed, and safety is always important to consider. When a substance melts, freezes, condenses, or boils, it is experiencing a phase change. When ice cream melts, or when you see condensation on the bathroom mirror after taking a shower, you are witnessing matter change from one phase to another. That change depends on a transfer of energy from one substance to another. The important question to consider in this lab is, how does temperature change during phase changes? In this experiment, we'll explore how temperature changes as ice melts, turns to liquid, and then warms. Then, you will analyze data to understand what happens during many phase changes. Use your observations and prior knowledge to write a hypothesis that describes how the temperature will change over time, as ice, a solid, changes phase and becomes water, a liquid, and then water vapor, a gas. A good hypothesis should take the form of an if-then statement, such as, if the temperature increases, then, well, you fill in the blanks. At least one day before the lab was done, we made a tray of ice cubes. We needed ice cubes to start the experiment. Before attempting the lab, we created a data table with the following columns: time in minutes, temperature in degrees Celsius, the state of the matter, and notes. First, we attached a binder clip to the top of our thermometer and placed the dowel rod through the loops of the binder clip. We then attached the dowel rod to the top of a stable object and taped the dowel rod securely in place. Then we placed the ice cubes in a small saucepan. We placed the thermometer in the ice, and then we started timing the phase change. To get the best lab results, we made certain that the thermometer was in the ice and not touching the bottom or sides of the pan. We were sure to record the temperature of the water this way, not the temperature of the pan. Over time, we observed the ice continue to melt. We kept taking temperature data during the phase change and the warming of the water. We'd complete the experiment by showing you more in this video, but that would be as exciting as watching ice melt. From the provided data, note that something interesting happens when water melts and boils. Think about what happened to the temperature when the ice was melting as compared with the time when there was only water. Finally, compare the results of your experiment with your hypothesis.
Okay, and so here is where you see the data that they actually got. So you can see the time as it went by, and you can see the temperature that they measured. Okay, smiley faces if that makes sense. Okay, so we're actually giving you the data today. Today, again, it's a super easy lab because I actually give you the data. Okay, so you'll watch the video, and then you'll see this data right here. Okay, and all you need to do from there is you're going to go ahead and chart it for me. And again, I'm going to give you a video that goes over that. So the next video I give you is going to answer questions 2 through 4 for you. And again, guys, we're actually using the same data, so your results should look exactly like mine. So as long as you just copy what I do, you should get 100% on your lab. Give me a thumbs up if that makes sense. Okay, again, the next video I'm going to give it to you right now. Okay, so this video right here should give you exactly how to do it step by step. Hello students, so at this point you have already answered question number 1 because that's what we did in class, or if you're watching the recording of the class, that's what we've already done. So now we're going to go ahead and move on to question 2, which is the graphing portion of our lab, and this one is a little bit tougher, which is why I'm going to take you through this step by step. Now, a reminder that for all of our labs in this class, you do need a Google account. If you don't already have one, it only takes 30 seconds to make one. All you need to do is go to accounts.google.com/signup. Make sure that you save your username and your password that you create because we do use the Google account the entire quarter. So again, if you haven't already done that, pause the video, make sure you get that done. Now here's what's going to happen. Really important. I'm going to take you through step-by-step questions 2 through 4. Now, as always, it's really important that after every step that I take you through, please pause the video, complete the step on your own, and then you can continue playing. So again, it goes, right, play the video, pause, do it, play. Pause, do it, play, and so on and so forth until you've actually completed the lab. If you try to just let the video play and try to keep up with the video, it gets very confusing and you might get frustrated. So I'm just trying to help you not get frustrated, helping you to strategize how you're going to do this well. So here's what's going to happen. These are our basic instructions here. So, and we do have our data over here. So what we're going to be doing is we are going to click on this link right here where it says google.com/spreadsheets so that we can go ahead and open up our Google Sheets. Now again, our basic instructions are going to be over here. So sorry, hold on, let me shrink this again. So our basic instructions are going to be right here. Okay, so we do need to create a new sheet and title it. So I'm going to go up here where it says plus over blank to start a new spreadsheet. Click on that. Again, pause the video if you need to do that. And then you're going to come up here to where it says Untitled Spreadsheet and go ahead and click on it, and that'll highlight it, and you're going to rename this. So this should be named the Phase Change Lab, and you should type your name here. Okay, so mine, for example, would be Mrs. Larkin, right? But again, make sure that you type your name here so that I know whose this is so that you get full credit when I grade this. Now, the next thing is we need to type our data into the sheet. Now, really important, you do need to make sure that you only include numbers in the actual data part. So right here, we're only going to include numbers, and we're not going to put any letters or words next to the numbers because otherwise it won't graph correctly. So I do have that data in your lab report right here as well. So I'm just going to go ahead and move this over here so that I can put that in. So first thing is your first column needs to be time in minutes. So I'm going to type time and make sure in parentheses I include the units, which is minutes. You need to make sure that's there. And then temperature in degrees C. Okay, and again, if you want to see this entire column, you can go ahead, just highlight this and move this to the side. Now, don't worry right now about the states of matter part. We will be including that in our analysis of the data. So for now, again, all we need are the numbers, and so the numbers are going to go in these first two columns. So again, this data, you should be copying it exactly as it's shown here because this data was provided to you in the video that we watched that showed how the experiment happened. So I'm going to type in this data. So this should be 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130, 140, 150, and 160. Okay, so type in your times exactly as you see them here, and then same thing, we're going to type in our temperatures exactly as we see them here. So I see 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. The temperature is 0 all the way up to 90 degrees, and then at 100 it becomes 4, 8, 16, 19, 20, 21, 21. Okay? So this is going to be our graph. This is what we're going to graph right now, okay? So again, don't worry about this third column. This third column, we'll analyze that in a little moment, a little bit later, okay? So first we need to go ahead and mark our graph. So what we're going to do is we're going to highlight from where it says time all the way down to the last number, 21 right here. So to highlight, just click and hold and then drag your cursor all the way to the bottom here. Then from here, we're going to click Insert and Chart. Please remember, if you need to pause, guys, again, make sure pause the video, do this step, make sure it looks exactly like this, no numbers next to the no letters next to the numbers, and then we can continue playing. So pause, play, pause, play. So I'm going to go to where it says Insert and then click Chart, okay? And let me go ahead and move this a little bit out of the way here. Okay, and again, guys, please make sure you move your chart so it's not covering up the data. That's really difficult for me to grade this if it's covering up your data. Okay, so from here, there's a couple things that we need to check here. We need to check that right here underneath x-axis, this does say time. If for some reason this doesn't say time, it'll say add x-axis. So I can show you what that looks like. So if it doesn't say that, click add x-axis. And then right here, you want to select time. So time all the way down to 160. So you're just copying all of this right here. So this should say time, okay? And then same thing underneath series, you should only see the word temperature. If you see both time and temperature, please click the three dots and remove the one that says time. It should only say temperature. And again, if for some reason something's missing here, you can click add series. So I can show this to you again, so I'll remove that. Oops, sorry. Once more, let me fix this one. So this should be the x-axis, and then this should be the y-axis. It should say temperature, and let me remove this one really quickly. So again, double check that the x-axis says time and the series says temperature. That'll make sure that your graph here is correct and that every other step works here. Now, before we move on to customizing this, we do need to go to where it says chart type. So we're going to change this from line chart, click on line chart, scroll down and change it to the first type of scatter chart. Okay, so now this is what this should look like. So we have a scatter chart right here. Perfect. Now from here, we're going to go underneath Customize, and we need to make sure that all of our titles and everything are correct. So your chart title just needs to be temperature versus time, so make sure you correct this. Again, you do lose points if you don't correct your titles, so this should say temperature versus time. And double check your other ones. So your horizontal x-axis, this one is correct, should say time with minutes in parentheses. If it doesn't say minutes, you do get a 0 on this title. And same thing with the vertical axis. It should say temperature in degrees Celsius. You should have units. Again, if you don't include those units, you do get a 0 on your vertical axis title. So make sure your titles look correct. They should look exactly like mine because honestly, we're using the same data. So all of our stuff should actually end up looking pretty identical. Now, this time we don't need to include a trend line. You will notice that a trend line wouldn't fit really well because trend lines are usually straight. So in this case, please do not include a trend line. You should not have a trend line here. And then just to go ahead and finish things up, we're going to go underneath horizontal axis, and we're going to click where it says treat label, or sorry, we're going to make sure that this right here is unclicked. So if for some reason this has a check mark next to it, please make sure it's unchecked. So this should be unchecked, okay? No check mark. And under vertical axis, same thing. There should be no check mark next to where it says treat labels as text. And last but not least, underneath grid line, we'll go ahead and fix this up just so it looks a little bit nicer. So under vertical axis, change the major grid line count to 10. And then same thing with your horizontal axis, change the major grid line count to 10, just so that we can see the curve a little bit better. Okay? Perfect. So that's all we need to do for our graph. So that looks perfect. Again, yours should look exactly like this. Then the last thing that we need to do, I'm going to kind of move this out of the way, is we do need to include our analysis of the data. Okay, so right here you can see that I have a chart here that you need to fill out. So underneath column D, go ahead and start this. So we're going to actually skip column C, just so that we keep our data separate. So under here, I'm going to type phase. And then my next column should be temperature range. Again, if you need to pause, please pause. Okay. Again, I'm going to move this over. Just click and drag to move that over. And then underneath F, I'm going to put change. Okay, just so we can see what happens to our water in this case. So underneath phase, I'm going to copy what I see here. So the phase in which we're only ice, the phase in which there's both ice and water, and the phase in which there's all liquid water. Water. Okay, so now what we need to do is we need to analyze our data here. Okay, so what we're going to see is we want to find what was the temperature range in which there was only ice. So we can look back at our data over here, and the temperature range in which there was only ice, right, was at 0 degrees, right? So we see that at 0 degrees, sorry, I should put in temperature range. This should be in degrees Celsius. Please make sure you include the units. Okay, so this should be degrees Celsius. So the temperature range for only ice was 0 degrees. Now, for the range in which there's both ice and water, you should take a look at the temperature that goes from ice and water all the way down. Okay, so in here, you would see, for example, that the temperature range goes from 0 to 0. So you would put in here 0, right? And then down here, you can see here that the temperature range for all liquid water begins to increase, right? So when we're all liquid water and we're adding heat to this liquid, to the solution, we can see it's going from a temperature range of 4 to 21 degrees. 4 to 21 degrees. Okay, so 4 to 21 should be right there. Again, please make sure you include degrees Celsius up here so that you know that these temperatures are in Celsius. Okay, perfect. So now that being said, what we can see is underneath change, you need to tell me how is the temperature changing. So your options are the temperature stays the same, it increases, or it decreases. So again, take a look at your temperature here and choose the correct term. So you should tell me if ice stays at 0 degrees the entire time, then you should say it stays the same. If the temperature increases while it's ice, which we can see here, it's definitely not. So I can give this one as an example, stays the same, okay? And then underneath ice and water, same thing. If it stays at 0 degrees, you would say stays the same the entire time. If it increases, you would tell me it increases. If it decreases, you would tell me it decreases. And then same thing right here under your last one for all liquid water, you should tell me what are these temperatures doing? Are they staying the same? Are they increasing or are they decreasing? Again, all that information needs to go right here. So this you should be able to fill out on your own. I'm not going to fill this out because this should be you analyzing the data. Okay, so once you have all of that done, that's it. That means you have everything done for this. It should look pretty much exactly like mine, except for making sure, again, that you have your yellow part filled out here. Sorry, one last thing, guys. If you do lose the menu over here to edit your graph, I do want to remind you, all you need to do is double click on the graph to open up the chart editor. Okay, sorry, I forgot to say that earlier. Now, the last thing that we need to do is we just need to get the shareable link. Now, again, if you give me the link up here that ends with edit, you will get a 0 because I cannot use this link. Okay, this is your personal link and I cannot see it here. Okay, so instead what you need to do is you need to go to where it says share and then click get shareable link and then make sure you copy the link. Okay, so from here it's super easy. All you need to do once you've copied the link is you'll right click and click paste. Other options are if you have a PC, you can do Control and V, press those two buttons at the same time. That'll also paste it. Or if you have a Mac, you can do Command and V at the same time. Click both of those at the same time on your keyboard and that will also paste the link in here. All right, and that is all you need for question number 2. And we're all set on question number 2 and it's saved here. So now I'm going to show you what we do for questions number 3 and 4. So for these steps, for question number 3 and question number 4, what we need to do here is we need to look at our data and make a conclusion, right? So our hypothesis for this experiment was if water changes phases from solid to liquid over time, then temperature will increase. So you should be able to say whether or not it's supported or disproved based on our data. So again, taking a look at your data here, all right, you should see, does the temperature increase? Right? Does the temperature increase as time goes on, as we're adding heat to our water? So you should be able to say supported or disproved. Now the tricky thing is here, guys, it's important to notice that while we can kind of see an overall trend, so I'm going to go ahead and figure this out with us, okay? So in this case, we do see that the temperature is increasing, right? It's going from 0 to 21. So we are seeing that over time, that our hypothesis is supported. So right here we should fill in the word supported. However, we do need to notice that during this time, it's not actually increasing the entire time. So you do need to state that here, right? That while it increases from 0 to 21 over our entire time here, for a good amount of time, it's actually not increasing. Remember, take a look at this time in which we are all, in which we are both ice and water, right? So this is the time from 10 to 90 degrees. So you should be telling me that during this time from 10 to 90 degrees, we actually didn't have an increase, right? During the time in which our water was melting, going from ice to water. So you should state that, right? So you should be able to see that overall, right, there's an increase in temperature, but it's actually only when we see that there's all liquid water. Okay, so sorry, let me highlight that here. Okay, so you should be able to explain this in different parts, right? So for parts of the experiment, is range. Temperature stayed the same, and you should be able to tell me what times, right? So so you should be able to say it happened from when. So for example, you should say here and see whenever it says stays the same, you should be able to explain that that was when we had only ice, when we had only ice and water, etc., etc. Okay, so right here you should be able to explain that right here. Temperature stayed the same when we had, you know, ice, only ice, ice and water, all liquid water, etc., etc. For parts of the experiment, temperature then increased, which is when we had blank, right? So you should again take a look at our analysis over here and say, where was the time in which temperature was increasing? So underneath the change column, wherever you see the word increasing, you should be able to explain to me what phase were we in which temperature was increasing. Okay, so again, you can definitely use this as your skeleton for how you're going to write this, but you do need to fill in these parts so that this is unique to your data that you see here, right? So as long as you fill in these parts and you don't just copy this exactly, right? Don't just copy the lines. As long as you filled in this part, you'll get full points. Okay, so it does say this warning that if you copy word for word, you'll get a 0. I don't count it as copying word for word as long as you fill in these parts with your numbers that you see here, and that you're making it your own by doing that. Okay, so again, fill this out completely and this will be good, and you'll get your full points here. So you should look at your data. You need to include numbers. Okay, you need to include actual numbers, otherwise you do get a 0 on the entire question. I don't even care if this part is filled out. If you're not filling out this part, you actually get a 0 on the entire part. I don't give half credit on this if there are no numbers. Okay, now question number 4, okay, is a follow-up question. Okay, so question number 4 is asking about how when we have a graph of temperature as phase changes occur. So this graph is actually much larger. It actually shows going from liquid to gas as well, so evaporation or boiling as well. So this right here is showing us how temperature changes as phase changes occur. Now what I want you guys to notice is that at the plateaus, which are the flat parts or the yellow parts here, something unique is happening, right? Where is the thermal energy going, right? It's pretty obvious to see that when we're in solid, liquid, and gas, these phases by themselves, that the thermal energy is going to increase the temperature, right? So we can see here during these parts, the thermal energy is increasing the temperature. However, during the melting and the boiling part, the thermal energy is not actually increasing the temperature. Instead, what we can see is that during these parts, these yellow parts, the thermal energy is actually causing the phase change. So all that energy is going in to just separate the solid molecules into liquid molecules, right? It's moving them further apart so that they become liquid molecules. But again, while we have two phases, temperature never increases. Temperature stays the same the entire time. The thermal energy is only going into causing the phase changes. Okay, so everything that I just talked about right there, you should be able to include right here. Again, there's no worrying about copying word for word because you just need to take what I'm saying and putting it down on paper, making sure that you understand that concept. That during these times right here, all that energy, that thermal energy, is just going to cause the phase change. It's moving the molecules further apart from each other, but not actually speeding them up, not actually making them hotter. Okay, so that's everything that you need to know for questions 1, 2, 3, and 4, and you are all set on that. Thanks so much, guys. Steven, just watch the videos. It'll make a lot more sense once you watch the videos, the 2 videos, okay? So the first video I just sent you again tells you how we did the experiment. The second video tells you exactly how to do questions number 2, 3, and 4. Cool. All right, and here is your last word, guys, and I will see you later. That lab is due at 4 o'clock, okay? So try to get it done before 4 o'clock. Thanks so much, guys, and I will see you all later. This is your last question for number 3. Bye-bye. All right, hello, guys.